In the late 19th century, chemists and physicists were working in a world they couldn't entirely see, looking to probe the hidden structures of matter. English chemist William Crookes observed something strange. When he placed structurally identical diamonds inside a vacuum tube, they emitted entirely different colors of light: pale blue, bright green, and apricot red. Inside this exact type of apparatus, he bombarded the minerals with a stream of electrical particles. He didn't fully understand the mechanics yet, but he was triggering a process that would bypass the limitations of traditional optics. To map the atomic world, normal light is physically insufficient. In standard photoluminescence, researchers use a laser to excite a material, but a laser is bound by the optical diffraction limit, known as Abbe's law. Because a beam of light cannot be focused into an infinitely small spot, it hits a broad area, illuminating multiple nanoscopic structures at once and returning only an averaged measurement. Visible light also lacks the energy required to excite electrons across the wide energy gaps, the band gaps, found in insulators and ceramics. The incoming photon simply doesn't carry enough kinetic force to make the jump. A focused beam of free electrons bypasses these physical limits. Using energized mass instead of photons, it can focus down to a single nanometer. Striking a sample with these high-velocity particles rips past the optical threshold, exposing internal crystalline structures that are otherwise invisible. Harnessing this beam required large, highly specialized equipment. Early electron microscopes were built to generate and direct these powerful particle streams with absolute precision. Today, the process is highly refined. A tightly focused beam of primary electrons is fired down a vacuum column directly into a solid specimen. Striking the crystal lattice, the primary electron scatters, kicking up thousands of secondary electrons. These collide with valent electrons, forcing them into a higher energy state. As these electrons inevitably fall back to their ground state, they release their excess energy as a photon. The violent atomic collision forces the silent specimen to broadcast a readable optical signal. We call this cathodoluminescence. This explains William Crookes's diamonds. If the gems are structurally identical, the light they emit under the electron beam should be identical. The variation in color comes entirely down to imperfections. Some glow is intrinsic. If there is a missing atom within the lattice, that defect creates a unique optical signature. Other variations are extrinsic. Foreign impurity atoms can wedge themselves inside the lattice. Introducing entirely different optical transitions, these trace elements light up brilliantly. To map this, modern microscopes use precisely angled parabolic mirrors to collect the emitted light, directing it out of the vacuum chamber and into photomultiplier tubes for analysis. For decades, you likely had this exact physics experiment sitting in your living room. A traditional 20th century television operates on the same principle. Inside the set is a cathode-ray tube. An electron gun at the back fires a beam through a vacuum to strike a phosphor-coated screen, converting kinetic energy into visible light. A perfectly uniform crystal structure is optically silent. It is the flaws, the impurities, and the structural damage that hold the true physical history of the material. Geologists use these glowing impurities to read deep time. By mapping the concentrations of trace elements like uranium and lead inside zircon crystals, researchers identify distinct growth zones, allowing them to calculate the exact age of rock formations from billions of years ago. NASA applied this same diagnostic technique to samples recovered from the Apollo missions, mapping the shock damage and mineral composition of lunar rocks to piece together the origins of the moon. The scale shifts from planetary history to human engineering inside sterile semiconductor fabrication plants. Manufacturers often face a severe problem with solid-state lasers and LEDs. A semiconductor material can appear completely flawless under standard inspection, yet mysteriously fail to emit light when powered on. Cathodoluminescence exposes the problem. It reveals threading dislocations, microscopic structural defects running through the crystal. These act as atomic dead zones, where electrons and holes recombine without releasing any photons, creating black spots that destroy the efficiency of the device. Identifying these deep-level defects allows engineers to refine their manufacturing processes. The exact method used to chart ancient geology secures the production of global electronics. Researchers are now moving into nanophotonics, studying how light and matter interact at scales far below the optical diffraction limit. Because the equipment captures detailed wavelength spectra and polarization data at every single pixel, the resulting datasets are massive. Artificial intelligence and machine learning algorithms are strictly required just to process the sheer volume of information. At a glance, a pure, uncut mineral is entirely dark, locking its internal history behind an opaque wall. But by harnessing the extreme kinetic energy of the electron, we bypass the limits of light. We force matter to speak, exposing the hidden fractures and foreign elements that shape our physical world.